Hello, folks. I hope you're all doing great. So, be welcome. So, today we are going to start solving. We are going to start solving for Bernoulli's equation. We are still talking about first degree and first order differential equations. So, in Bernoulli's equation, so we are going to analyze, different types of the Bernoulli's equation, like different form that a equation, a linear equation can be solved. So just to you to remember, because that Bernoulli's equation, it is a linear. It's like it's a different way, to write a linear differential equation, because Bernoulli's equation, it is an equation that it is not directly given in a linear differential equation, but we can reduce it to a linear differential equation. So the, how can I say, the general form of this Bernoulli's equation, is this one. So again, I will say Bernoulli's equation are those equations that are non-linear but can be reduced to a linear differential equations. And they have the form, they are presented in this form. This is the form of Bernoulli's equation. And we are going to see, how to reduce this Bernoulli's equation into a linear differential equation. Then we are going to solve some of this exercise, just some, because some will remain for your practice and things like this. Now see, any differential equation that can be reduced in this way, in this form, I can call like as a differential, as a Bernoulli's equation. It's a differential equation that can be reduced to a linear differential equation. So here we have the form of Bernoulli's equation is dy by dx plus p of x times y equal to y raised to n qx. So as we know, we have just to reduce this equation that is non-linear. Why it's not linear? Very simple. Here the derivative of y is linear, and here we have y linear. But the point is that y raised to n, it's not linear. So it is not linear, but we can reduce in a linear form. This is the concept of this Bernoulli's equation. So the point is how to reduce to a linear form, how to reduce this in a linear form. So to reduce this expression in a linear form, I will solve in this side. I will just reduce in this side. So to reduce this one, so what do we have to do? The first thing is just, let me write this one. Hope you all can see from there. Hope you all can see from there. So what we are going to do, so here we have dy by dx, dy by dx plus p of x, y equal to y raised to n, and here q of x. Nice. So what do we have to do? So we know that we want to transform, we want to make this differential equation look like this: dy dx plus p of x, y, equal to only q of x. This is a linear differential equation because differentiation of y is linear and y is linear also. Y raised to 1 differentiation is with the order 1. So 1, 1, this is linear. This is the objective. So the main objective here is to keep this q of x as a function of x only. There must not have any y or something like this, because if you see, this y raised to n is the element that is making this expression or this entire differentiation equation not linear. So what's the first step here? So the first step here is just to divide this one, take this one out of here. The greater n, y raised to n is greater than 1. So take this one here, divide it all by y raised to n. If you divide it all by y raised to n, what you're going to have? Y 1 upon y raised to n dy dx plus here p of x, then here you get y raised to 1 minus n is equal to q of x. Okay, yeah, just this term. As you see, you can see y raised to n, y upon y, 1 upon y raised to n, okay, p of x and this, so on. So now what you have to see, remember, okay, the general form of Bernoulli's differential equation, it is this one, okay, this one. Whenever I can get f of y here multiplying, okay, dy by dx, and f of y here, it is the first derivative of this guy, so I can reduce it in a differential, in a linear differential equation. So see here, this we have y raised to 1 minus n, and here we have this one. Okay, so this expression, okay, derivative of this expression is equal to derivative of this one, is equal to this one. Okay, as we can see, f of y, okay, f of y derivative, if I derive f of y, I will get here as a function like this. Okay, let us try to see whether this is true or not. So y raised to y minus n, I will make this one, I can make this one and say u. Okay, just okay, apply this supposition. Let y raised to 1 minus n equal to u. Okay, u here is a function of x also, okay, as y is a function of x too. So now apply derivative of this and derivative of this. So what you are going to have here, if you derive with respect to x, it will be 1 minus n. Okay, just apply chain rule. Okay, 1 minus n, 1 minus n, then minus 1, okay, then dy by dx is equal to du by dx. As I told you in the beginning, u is a function of x too. So what you're going to have here, okay, see, if we find that derivative of this guy, okay, if the derivative of this guy can be found in this way, okay, if this derivative, if we can derive this expression and get this expression here, as you can see here, so this can be reduced in a linear differential equation. This is what we are going to see. So minus 1 and plus 1, this will be 0. Minus 1 plus 1, 0. It will be minus 1 here only in the exponent of y. So it will be 1 minus n, okay, time 1 raised to minus n, okay, dy by dx equal to du by dx. du by dx. Now, what's the next step here? The next thing to be done, okay, the next thing to be done is just to hold this one down. So dy by dx, this guy, it's minus, so it will be the opposite, 1 by n, okay, 1 by y raised to n. Then we have this expression, this is a constant, okay, this is a number, 1 minus n is a number, can be put in that side, okay. So we are going to have 1 by 1 minus n du dx. Now see, okay, as we can see, by deriving this term of that is multiplying by px, okay, by deriving this term, we got this expression here. Okay, we got this expression. So according to the general form of this Bernoulli's equation, this equation can be reduced to a differential or to a linear differential equation. So that's why we do this one. So what we do then the next thing is just we're just to substitute this expression and this expression in the main expression here. Okay, I'll call this 1 and I will call this star and I will call this double star. Okay, so what you have to do now, just put star and double star into 1. Okay, star and double star in 1. What you are going to have, okay, y 1 upon y raised to n dy dx is equal 1 upon 1 minus n du dx. So it is 1 minus n du dx plus p of x. Then what is y raised to 1 minus n? It is u. It is equal to q of x. Q of x doesn't change. Okay? Now, if you can see this, this is actually a linear differential equation. So the only thing you have to change here is just to send this one out. Okay? This is 1 minus n, right? Multiply everything by 1 minus n. So this will be du by dx, okay, plus, okay, 1 minus n p of x, then u is equal to 1 minus n q of x. Okay, yeah, just like this. As you can see here, okay, this equation is reducible to a linear differential equation. Okay, this is what we mean by Bernoulli's equation. Okay, so in a general way, okay, any equation that can be presented like this, okay, that can be present. If you can organize an equation in this form, a differential equation in this form, like f of y dash dy dx plus p of x f of y equal to q of x. So just do this substitution directly. If this is true, then do this substitution, f of y equal to u. Okay, then find the differentiation, just find the differentiation of this and this with respect to x. If it were y, with respect to y, and so on and on. Okay, this is what we are going to see now. Okay, this is what we are going to see now. Okay, let me just take a while. Okay, as we did there. Okay, please do not forget about this. Okay, what we did here. Okay, so we are going to use now. We are going to solve problems so that you can have more ability to understand and more. You can just get more. How can I say, more enlightened in this. Now that it is true, I will erase and I will start solving some problems here. Okay. Okay. So here we go for our first exercise. Okay. What we are trying to see, or what we will try to solve, is just this expression here. See, here I cannot say that this is a linear differential equation. Okay, I cannot say directly this is a linear differential equation, but let us see if there is possibility to transform this equation in a linear differential equation. But first, if knowing that here x, suppose here it's not a linear differential equation, suppose here you have the dy by dx. So dy by dx, it's a linear derivative, nice. By x is not linear derivative, neither y is linear itself. Okay, so what should we do here? But there is a relation between y and x, so we will try to solve with y. Okay, solving for y with respect to x. Okay, we will try to organize in order to see whether we can get this expression or this expression in a general way. Okay, so how to make it equal itself? Okay, to make them equal, that's the point. So it must be dy by dx, then all these members, you can come here or it's up on you. So see, as you can see here, we have dy by dx plus pxy, right? Pxy, polynomial of x times y, then y raised to n qx. See, this y raised to n is greater than y. So here I will also solve for this one. This is greater than y. So this can remain here, okay? This can remain here and this can come here. So I'll get this xy equal to x cubed and y cubed. Is that okay? Because this one, comparing with this is y raised to n, this is y, this is px, and this is dy dx. Now what's the next step? The next step is nothing from here, okay? This term here must get out of them, of here. You have to take this out, like you did here, in this way, okay? As we did in that simplification in the beginning, okay? This term must get out. So I come here and I divide by y cube, and here y cube. So what will I get? I will get 1 by y cube dy dx plus x times y minus 2. Okay, this and this will be cancelled out, so this will just 1 minus 3 minus 2. Then here you remain the term in x only, x cube. So this one, as you can see, this looks like a Bernoulli's equation. This looks like in a form of Bernoulli's equation. So what's the next step now to see whether this is Bernoulli's equation or not? The next point here is what? It's just to do the derivative, okay? Just find whether this f of y is derivative, okay? Whether this f of y, this expression, is, okay, is derivative of this one. Like if I derive this one is equal to this one, just fine. So how to find? Make u equal to y minus 2. Then what's the next step? Du by dx is equal to this one. If I derive this one with respect to x, it will be minus 2, okay, minus 2y raised to minus 2 minus 1, then dy by dx. Just apply chain rule. So what you're going to have now, du by dx, okay, du by dx, okay, is equal to minus 2 y raised to minus 3 dy by dx. So this y raised to minus 3 is the same as 1 upon y raised to 3. So this 2 is constant, can come here. So what we are going to have, du by dx minus, okay, minus 1 by 2 is equal to 1 upon y cubed dy by dx. You see, this is double dash, double star, this will be my star, okay, and this will be my equation number 1, okay, can call this equation number 1. Okay, now what's the next step? So here just substitute, okay, just substitute 1 by y cubed dy by dx. Okay, this is in, actually this is like in Bernoulli's equation. So from there you just have to solve this one. If you substitute, okay, substitute star, okay, substitute star and double star in equation 1, okay. Let us substitute. How will it be? It will be minus 1 by 2 du by dx plus p of x, plus what? Plus x times u equal to x cubed. Okay, now from here it's very easy, so just multiply everything by minus 2, multiply everything by minus 2, you are going to have du and dx, okay, du dx minus 2x times u equal to minus 2x cubed. Okay, the next step here, what's the next step? Very simple. So just now that you know that this is a linear, because this u, differentiation of u with respect to x is linear and u is linear, so you have just to solve for this one. So what you have to solve, how do you have to solve? This is p of x minus 2x, and this is q of x is equal to, this is q of x, maybe I'm just getting so long there, this is q, okay, q is minus 2x cubed, and p is this, so just find what is your integrating factor. Integrating factor will be Euler raised to this p of x, okay, raised to p of x. What is p of x? It is minus 2x dx Then you can find what is integration of this guy. Integrating factor of this one, okay, just find this one. What will be integrating factor? It will be Euler raised to minus x squared, okay. Euler raised to minus x squared, because this integration is minus x squared by 2, 2 by 2 will be cancelled out, so minus x squared. Now that you know what is your integrating factor, okay, here the given solution, okay, the given solution will be, okay, we are running out of space. I will write the given solution up here. We know what is given solution, okay. For linear differential equation, we know that the solution is what? Is u, that is dependent variable, time if equal to integration of if time q, okay, plus c. This is what we are going to see, okay. Just put it there. What is u? U is u, if is Euler minus x squared is equal to integration if, again, Euler minus x squared, then time, we have there, what is q? Q is minus 2x cubed, so minus 2x cubed, okay, dx. Then just solve this integration, okay. If you just apply just some, if you just apply this, what's the name of this one? You have this integration here. This is minus 2 integration of Euler minus x squared, and here you have, you can take only minus 2, it's fine, minus 2, okay, time x cubed dx, okay. Yeah, then you can just solve this exercise. I'm running out of space here, but anyway, I will try to. Okay, so I had no much space there, so I will just solve from this space. Okay, I will just solve here this integration. Now see, okay, I have not that much space here, so I will solve for this one. So see what will be the next step here. See, here we have this expression, right? So how to solve this integration? You can apply differentiation like in this way, okay? You can just come directly and apply, what is this, like integration by parts, okay? You can just find integration by part of this one. Just find what is integration by part of this expression. Suppose here, here you will have an expression like this, okay? You can solve by parts, but here I will use, I will use a substitution directly, then I will solve by parts also, okay? It's up on you, okay? It's up on you. So here by parts, or how can I say? Okay, so let us solve, okay? So for this one, I can do this one, I can do this, this operation, like make, just let Euler raised to minus x squared, okay, be equal to t. Okay, just do this substitution. So then find what is x squared directly. Okay, you can find what is x squared or whatever you feel like. But let us just solve first. Okay, then find the derivative, differentiation of this and this. This will be, if you differentiate this one with respect to x, it will be minus 2x. Okay, minus 2x. Then here you'll get Euler minus x squared, okay, dx is equal to dt. Now we have what is dt, okay. Then we can just send this minus 2, there is a constant, x Euler minus x squared dx, and here dt by minus 2. It will be only this one, negative in this expression. Now see, this one is what we got, okay. This is substitution for the differentiation term. But see, we have x Euler raised to minus x squared, okay, and here it is here. If I split this x cubed, I can have x and x squared. So it means that I can find here directly what is x squared, then substitute in there, okay. So if I just apply ln here and ln here, I will get minus x squared is equal to ln of t. So this one means that x squared will be equal to minus ln by this one. Okay, so I will pick up this expression, these two expressions, and I will substitute this one. Okay, how to substitute? Then I will get u times Euler raised to minus x squared is equal to minus 2. Then it is Euler raised to minus x squared times x dx times x squared. This is the same. X squared times Euler minus x squared times x dx. Okay, this expression here is minus dt by 2, and this expression here is minus ln of t. Okay, then just substitute in this. So what you're going to have, Euler minus x squared, this will be minus 2 integration of this guy. This will be minus ln of t time minus dt by 2. Okay, so what you're going to have, this expression here, minus 2 and 2 will be cancelled out, so it will be minus integration of ln t dt. Okay, and this integration here, if you just find this integration by part, just apply by parts, integration by part. So you will be here. The integration easy to derive. It will be u, and the integration easy to how can I say? The function easy to derive is u, and the function easy to integrate is v. So here you will split this one into function. Ln of t is easy to derive, and dt is easy to integrate. So integration of dt, and here ln of t. Okay, ln of t is easy to derive, this one. So du will be 1 by t. Okay, dt by t, and this integration v will be equal to t. So if you just solve this one, okay, then substitute in there, you are going to have this expression in this way. Okay, solution will be minus, okay, minus what? T ln of t minus 1. Okay, just like this, minus 1 and t. Okay, just in this way. This will be the solution. Then what you have to do, substitute. What is t? Okay, just go back there. T, ln of t is x squared. Okay, but minus ln of t is x squared. It means that ln of t positive will be minus x squared, and t will be what? T will be your Euler raised to minus x squared. So just substitute minus Euler raised to minus x squared. Okay, what is ln of t? Minus x squared minus 1. Okay, so this, as we know, it is u times Euler raised to minus x squared. Okay, so here, okay, plus c, okay, it's fine. Now see, this is u times Euler minus x squared. Now go back to the substitution. You know that u is what? What is u? U is also y raised to minus 2. So it will be, in the end, y raised to minus 2 Euler minus x squared is equal to minus positive Euler minus x squared, okay, x squared plus 1 plus c. Okay, this is the solution for this integration, for this differentiation equation. Okay, you can write in this way. Okay, you can write in this way, or you can just do some change. It's up on you. Okay, from there it's okay. Now let's just solve one more exercise. Okay, just one more exercise so that we can feel it's okay. Okay, now suppose we have a different exercise here. Suppose we have an exercise like this, in this form, okay? Like we have dy dx, okay, plus 2x tan inverse of y, okay, minus x cubed and here it is multiplied by 1 plus y squared is equal to 0. How to solve this exercise? How to solve this one? First thing you have to understand is, okay, checking, okay, this is dy by dx, and if you see, okay, you have to think in this way. So like you have to have a term that must be without any y, okay, this term here, suppose it is with y, okay, so it must be without any y, okay. You have to reduce this differential equation. You have to try to reduce, because some equations are not reducible, okay. Just try to reduce. Okay, that's this one and this term. So how to do this one? That's the point. See, here you have y, 1 plus y squared. So you can multiply this by this and this by this. It's okay? So you can do in this way. Very easy. It's okay? dy by dx plus 2x tan inverse of y times 1 plus y squared. Okay? Then minus x cubed. I'm just distributing this and this and this and this. Okay, just distribute them. This 1 plus y squared is equal to 0. Now the next step is, okay, here I have tan inverse of x of y. Okay, tan inverse of y. And this x is linear. It's okay, it's fine. And here we have x cubed. Okay, 1 plus y squared. So what should we do to transform in this expression? Now think. Can you transform in this way? No. Actually, it will give a very, very, very complicated way to transform in this way. So the next thing is you have to think on a general form of the Bernoulli's differential equation. The general form of this Bernoulli's equation is you have to reduce the equation that they gave you in this form. Okay, you have to find what is f of y, so that f of y dash, derivative of f of y, with dy dx must be in this form, and here you can have px of f of y. So think, you have tan inverse of y. Derivative of tan inverse of y is this expression, but in an opposite side. Like when I derive this tan inverse of x, this is 1 upon 1 plus x squared. Okay, so this is what you gain. You will gain here. So to make this expression here, like this in this form, so the only thing you have to do is just divide this one, because tan inverse is the opposite of this part here. So divide it all by 1 plus y squared. And in this way you get only an expression of x also, that will be your q of x. Okay, and here you have only 2x, then tan inverse of x, that will be your f of y, and then here you get 1 upon 1 plus y squared, that will be your f of y dash, that is tan inverse derivative of them, derivative. Okay, so divide it all by y square. Okay, y plus y square, 1 plus 1 plus y square. Okay, just in this way, dx plus 2x tan inverse of y, then minus x cubed is equal to 0. Just in this way, divide it all in this way. Then see here, this is tan inverse. Derivative of tan inverse is this. So I can just go and say u is equal to tan inverse of y. Then from here du by dx. U is always a function of x. Du by dx will be dy upon 1 plus y squared. Okay, sorry, okay, 1, okay, this will be 1 dy by dx. Okay, now that it is found, just substitute in this and solve this differential equation. What you are going to have? You are going to have an equation, okay, like this. Let me just put this continuation point, this one. So you are going to have an equation like this. Substitute this expression and this, okay, in this equation here. See what you're going to have, okay? What you're going to have, this expression, du by dx, okay? It is this and it is this. Then here plus 2x tan inverse of u is u, tan inverse of y is u, minus x cubed. Okay, this minus x cubed, as it is a term of x only, can go down outside. It will be your x, your cube. Okay, x cubed will be your cube. So this expression here is your p of x, and this one is your q of x. Okay, in this form it is reduced. Now you can solve. Okay, first you have to find what is your if. If will be Euler integration of p of x dx, Euler integration of 2x dx. This is Euler x raised to Euler raised to x squared. Then after finding this, what is the given solution? Okay, given solution will be what? Will be your independent variable u times if is equal to integration of if times q, okay, dx. Then just solve this equation, this expression. What is u? U is u, okay. If is Euler x squared is equal to if. What is if? Euler x squared. Q is x cubed dx. If you see this expression, this is the same expression that we got last time. If you remember that integration that we had last time, if you do the same process, okay, the same process, in the last equation we got something like this, okay, we got something like this. If you do the same process, okay, just do the same process, Euler x squared and x cubed dx. How to solve this one? Make your u x squared is equal to t, okay. If it is equal to t, then find this integration, derivative of this and derivative of this. This will be x twice, okay, square dt by 2, okay, dt by 2. Then you can just solve. Here you have x squared will be ln of t. So yeah, in this way you can just find that the solution will be the same, okay. We will 1 by 2 t ln of t minus 1, okay. The solution for this one will be almost the same. So you can then, yeah, you can just solve, and it's okay, it's fine, okay, it's fine. So just solve this one. This will be 1 by 2 t ln this minus 1. So what is, then just substitute what is t. This will be 1 by 2 Euler x squared, t is x squared, t is this one, time ln is x squared minus 1, okay. This will be your solution for this expression, for this solution, this equation. So u times Euler x squared, and this is 1 by 2 Euler x squared times x squared minus 1, okay, plus c and plus c, okay. Hope you can see this one, and this is clearly done. Now what is u? Just go back, okay, go back to your substitution, We said in the first substitution that u is equal to tan inverse of y, so it will be tan inverse of y, Euler x squared 1 by 2 Euler x squared minus 1 plus c. This will be your given solution, okay. This will be your given solution, okay. Tan inverse of this guy, and so on and on. So thank you very much.